And really big black holes, which are bigger than the entire solar system, have entropies into the 10 to the 80th, 10 to the 85th or something. So these are enormously entropic entities. But Bekenstein didn't just tell us that. He told us something about the structure of the interface, the horizon of a black hole. And this is what he told us. You can compute entropy in bits just by using log space 2 instead of log space e, natural logs. And that's just multiplying the natural log by about 1.4. So we can write the entropy of black hole in units of bits, and it's about A over 6. So what does this mean to say that we can think of the entropy in terms of bits? What it says is that we can think of the interface in terms of a bit array. And we can think of all of these bits as encoded on this interface at a density of 1 bit every roughly 6 Planck lengths squared, 6 Planck areas. So this is an incredibly dense encoding in a black hole. And it's an interesting idea about black holes, but what gets really interesting is what happens when you generalize it. And of course, physicists are prone to generalization, and that's what happened next. Gerard 't Hooft, almost immediately thereafter, on the basis of Bekenstein's work, formulated the holographic principle. And what the holographic principle says is we can think of any system as approximately a black hole. And the only approximation is the encoding density. The boundary of any system encodes the information that we can get about the system at some density. And the density is less than the density for a black hole because we're not black holes. And this rules out a lot by limiting the amount of information that you can extract from a system to the amount of information that you can actually write on its boundary. And one of the things that it rules out is knowing the geometry on the inside of the system. And 't Hooft put it this way, which I think is a brilliant thought experiment. He says, look, the metric inside this system can be so curved, effectively the space-time inside the system can be so curved that you could stick an entire universe inside. And we never know, because it wouldn't change the amount of entropy, number of bits that are encoded on the boundary. So the inside geometry can be anything, and you can't find out by looking at the outside of the system. Now, the holographic principle almost follows from classical physics. There's Euler's theorem, which tells you about 1 over r squared forces, and you can think of the force as penetrating the boundary at some density. And the difference between Euler's theorem and the holographic principle is just that the density in classical physics can go to infinity. And in the holographic principle, it can only go to this maximal density that's achieved by a black hole. Why? Because if you try to get any higher and more information, the information gets sucked into the black hole and you can't get it out. So the holographic principle becomes a guiding principle for thinking about any physical system and what it means to extract information from a physical system. And in fact, and we'll talk about this next time, you can say exactly what the information encoded on the boundary of any system is. What I'll go through next time is seeing that the information that's encoded on the boundary is a specification of the energy that's being exchanged by the by the interaction, which of course is linear in the number of bits. It's just counting the number of bits. Okay, so with the holographic principle, we now have a complete new science about systems that are exchanging finite discrete information across a boundary by encoding that information on the boundary and then reading the information off the boundary. So here's a new way of thinking about physical interaction. Alice writes a message on her boundary with Bob, and Bob reads the message off the boundary and then writes his own new message, which Alice then reads. And of course, that's what's happening right now. I'm writing information by speaking on an interface, which is effectively the internet, and you're reading that information off the internet by listening to it. And when we get time for questions, you'll be writing information on the internet, which I'll be reading. Now, the key thing about this new science is that it's topological. It's about connectivity across some communication channel, which we represent as a boundary. It's not geometric. So it doesn't assume anything about space-time. So it allows us to build a model of space, in particular, as an emergent phenomenon. And it allows us to see time as not some absolute external abstraction, but something that the communicating agents measure for themselves. And so they each act in their own time. And we get a very natural measure of time in terms of how many bits I see coming across my boundary. And again, we'll talk about that in the next couple of sessions. So quantum information theory looks very different from the physics that came before, not because it's adopted a new formalism, the tools of quantum theory. It's because it's entirely changed the thinking about what physics is and what it's about. And replace this idea of forces and balls banging into each other and all of that with the idea of communication between agents. And of course, that's familiar from an active inference perspective. So we can now back up a little bit to see what they were doing in classical physics during this period. This is just a slide quoting Wheeler, who, of course, is the most radical in terms of, and pithiest in terms of formulating these ideas. But here's his characterization of this new physics. It's not reductive. All of the reasoning is circular. You don't have smaller things and then yet smaller things and then yet smaller things forever. There are no laws. So what you see on the interface is a message. It's not something that's governed by laws since the beginning of the universe. There's no continuum. So there's nothing described by real numbers. It's all described by integers. Everything's done in finite dimensional spaces. And finally, and most importantly, there's no space-time box in which things happen. So think of how radical this is. It means there's no Big Bang. There's no Big Rip. There's no bouncing universe. All of those ideas are out the window because they're classical and they're about space-time. And what the new physics wants to do is derive space-time out of basically users' experiences. So the agents here are all observer participants in Wheeler's language, but what that just means is agents that want to communicate, and it's their communication that gives rise to physics. So now we'll go back to classical physics. And what was happening, or one thing that was happening in classical physics at that time, was a lot of thinking about stochastic causal networks. And Pearl realized that if you have any stochastic causal network that's unidirectional, then around any node, you can draw what he called a Markov blanket. And a Markov blanket is just the set of nodes in the network that absorb all outside causation and then transmit that causation into whatever node you're interested in, and then absorb all causation coming from the node you're interested in and transmit it to the rest of the world. And so we can redraw that in part B here, and it should look very familiar. A Markov blanket is just a classical physics way of talking about a holographic screen. And the number of nodes in the Markov blanket, or in particular, the number of degrees of freedom times the number of nodes, is just the number of bits that flow across that Markov blanket. So it's the entropy of the effective holographic screen. So all these ideas were reinvented more or less independently within classical physics. And it was from this classical physics background that Carl Freston came up with the idea that a Markov blanket defines a persistent, at least from an Active Inference Institute point of view, everyone is familiar with, because it's the foundation of the idea of active inference. Any system that persists through time does so by making sure that it doesn't dissolve into its environment. Well, what does that mean? It means that it persists through time by maintaining the integrity of its Markov blanket, or the integrity of its boundary. So this, of course, is just a tautology, but it's a very interesting and very productive tautology, because it says that any system is using the information it gets on its boundary from its environment to build a model of how its environment behaves. And then it uses that model to act back on its environment to test and refine its model. And again, as Popper told us, this is just what science is. So what the free energy principle really tells us is that all systems are agents that are doing science all the time. So physics is effectively not just the study of communication, but it's the study of agents doing science with each other, pairs of agents who are trying to figure each other out by their communicative exchanges. So that's the history of how we got from 1850s thermodynamics to the free energy principle. And how the free energy principle connects to these very deep and extremely radical, especially within context, ideas in quantum theory and quantum cosmology and computer science, all of which tell us that the world we see is a projection that's being written on our boundaries by a process that we have no access to except the procedure of active inference, or the procedure of science, which is to formulate predictive models and test them by doing things in the world and seeing how the world responds.